Welcome! Today we're diving into the PIC16F877, a real workhorse of a microcontroller. And we're going to focus on its nervous system, how it actually talks to the outside world. We'll be looking at three really powerful serial protocols that are quite frankly the essential toolkit for any embedded systems engineer. Okay, so here's our game plan. First, we'll tackle the big why. Why bother with serial communication at all? Then we'll get into the nitty-gritty of USART SPI and I2C. And we'll finish up with the most critical part, the trade-offs, so you can walk away knowing exactly how to choose the right tool for your next project.
So, first things first, let's talk about the fundamental problem. You've got this amazing little brain on a chip, right? But how do you get data into it and out of it without creating an absolute nightmare of wires on your circuit board?
And this image says it all. Just look at that tangled mess on the left. That's parallel communication for you. Every single bit of data needs its own wire. It just eats up your precious I/O pins and makes for a really complex, noisy board. But now, look to the right. That's serial. It sends all the data, one bit at a time, down just a couple of lines. It's clean, it's efficient, and honestly, it's going to make your life as a designer a whole lot easier. Okay, let's jump into our first protocol. USART. You can think of this as the most basic, direct, one-on-one conversation your microcontroller can have. It's perfect for simple, dedicated connections. The real beauty of USART X is just how simple it is. You've got two wires, that's it. One for transmitting data out, the TX pin, and one for receiving data in, the RX pin. And since they're separate, the chip can actually talk and listen at the exact same time. We call that full duplex. But wait a second, take a closer look. What's missing? There's no clock line. So how do they stay in sync? Well, that's because this whole thing is asynchronous.
So if there's no clock, how on earth does this work? It all comes down to this really clever data frame. See that start bit? That's where the line goes low, and it's basically a wake-up call shouting, hey, data is coming. After that, both devices have to rely on a speed they agreed on beforehand, the baud rate, say 9600 bits per second. They use that rate to sample the data bits at just the right moments. A final stop bit says, okay, we're done. It's all about timing.
All right, next up is SPI, the Serial Peripheral Interface. And you turn to SPI when your project philosophy is basically just one word, speed. This is your go-to for high-throughput data transfer. So how does SPI get all that speed? Well, it adds back that dedicated clock line, SCK, which acts like a shared metronome for everyone on the bus. Now the data is perfectly synchronized as it goes out on the serial data out line and comes in on the serial data in line. This synchronous method lets SPI absolutely scream along at up to 5 megahertz. But you can probably already see the trade-off, right? More speed is costing us more wires. Now, this brings up a really important question. How does the master pick which slave to talk to? With SPI, the answer is kind of brute force. It's pure hardware. The master needs a separate slave select pin connected to every single slave. To talk to one, it just yanks that specific pin low. That one device wakes up, and all the others just ignore everything. We call this hardware addressing, and while it's super simple, it gets really expensive on your pin count, really fast. And that brings us to our third protocol, I2C. Now, if SPI is the sprinter, all about raw speed, I2C's philosophy is totally different. It's all about scalability. I2C is designed to create a whole network of devices using the absolute minimum number of pins. And this is the magic of I2C. Seriously, look at this. You've got a master and a whole bunch of slaves, and they are all sharing the exact same two wires, SCL for the clock and SDA for the data. That's it. This is how you can build a network of up to 1,023 devices, and it'll still only take up 2 pins on your microcontroller. It's just incredibly efficient. So how does it juggle all those devices with just 2 wires? Well, instead of all those physical select lines like SPI, I2C uses software addressing. The master starts the conversation by broadcasting a packet that contains a unique binary address. It's like calling out a name in a crowded room. Only the one slave with that exact matching address is supposed to answer. And it answers by pulling the data line low for a moment. That's the acknowledge bit, or ASCK. It's basically a digital handshake. Okay, so we've covered the how for each of these protocols. Now for the really important part, the which. As an engineer looking at a blank schematic, how do you decide which one of these tools is the right one for your project?
It really boils down to the addressing philosophy. Think of it like this. USART is an implicit, one-to-one connection, like a dedicated pipe between 2 points. SPI is a one-to-many system that uses hardware, a physical wire, to act like a railroad switch, directing the flow of data to one track at a time. And I2C, well, that's a one-to-many broadcast system, like a PA system calling out a specific name and waiting for that person to respond.
And the reason these different approaches are even possible is all about timing. Asynchronous systems, like our friend USART, are kind of flying blind. They need that rigid, pre-agreed timing and those framing bits to even function. But synchronous systems like SPI and I2C, they have that shared metronome, that clock signal, which keeps every bit perfectly aligned. That's what allows for much higher and more flexible data speeds.
And all of this leads to the core engineering trade-off, which this graph just lays out perfectly. There's no free lunch here. There is no single best protocol. USART lives down here in the low-speed, low-complexity corner. SPI is way up here, giving you maximum throughput, but you are going to pay for it with more pins and more complex wiring. And I2C? It hits that sweet spot right in the middle, giving you decent speed and massive scalability for very little overhead. So let's just boil this down into some practical examples. You just need to print some debug text to your computer? Easy. 2-wire USART is all you need. What if you need to build a whole network with a dozen different sensors, maybe an OLED display and a memory chip? I2C is absolutely your best friend. But if you need to stream high-frequency data from, say, an analog-to-digital converter, nothing is going to beat the raw, unadulterated speed of SPI.
At the end of the day, serial communication is the nervous system of your embedded project. By really mastering these 3 distinct design philosophies, the point-to-point simplicity of USART, the raw speed of SPI, and the incredible networking power of I2C, you literally unlock the ability to connect your PIC16F877 to just about any sensor, display, or peripheral out there on the market.
And that brings us to one last really powerful idea. We've been talking about these as if you have to choose one, but here's the kicker. The PIC16F877 has dedicated hardware modules for all 3. So the real question isn't which one to choose, but how do you combine them? How would you tackle a problem like this, connecting a high-speed camera that needs all the bandwidth of SPI and a low-speed temperature sensor at the same time? That's where the real creative engineering begins.